Andrea, and this is AP Physics C Mechanics FRQs. Today we're going to be talking about 2019 Set 2 Question 1. So the question says, blocks of mass m and 2m are connected by a light string and placed on a frictionless inclined plane that makes an angle theta with a horizontal, as shown in figure 1. Another light string is connected to the block mass m to a hanging sphere of mass M, passes over a pulley of negligible mass and negligible friction. The entire system is initially at rest and in equilibrium. Overall, the system is blocks of mass on a ramp with pulleys. It's currently at equilibrium, but it can start moving. So overall concepts, definitely we're going to talk about equilibrium, and with equilibrium net forces is 0 because it's not moving, its acceleration is 0. So we're maybe going to use Newton's laws or force diagrams. So question A, on the dots below that represent the block mass m and a sphere of mass M, draw and label the forces, not components, that act on each of the objects shown. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, this is your classic force diagram. So we need the direction of the force. The question didn't specify that the magnitude of the arrow correlates with the magnitude of the force. So you can have any length arrow. I like to start with the easy component first. So we're going to start with sphere M. So as you can see, sphere M only has two forces acting upon it. One of them is tension force with the string pulling on it, and one of them is force due to gravity. So I like to draw the tension force going straight up, and make sure to label it tension 2 as it's connected with this string, and force due to gravity. For force due to gravity, I usually like to label it FG, but since we have to draw two force diagrams, that can be confusing. So FG can also be written as W, or can be written as mass times gravity. So the sphere's mass is capital M times G. Okay, going to the small block of M, one thing to notice is that the inclined plane is frictionless, so we don't have to worry about any friction. Okay, so each object definitely has its force due to gravity, and there's two strings pulling on M with tension 2 and tension 1. Since block M is also resting on the ramp, it will also have a normal force. So we're going to draw the easy tension 2 and tension 1, make sure that they are parallel to the inclined plane's angle, and make sure to label them clearly. So block M has a force due to gravity, and that's always facing towards the ground, so make sure it's pointing downwards, and we're going to label it mass times gravity. So the block also has a normal force, and normal forces are always perpendicular to the surface the object is on. So it's going to be perpendicular to the plane, and we're going to label it Fn, and that is your answer for part A. Part B. Derive the expressions for the magnitude of each of the following. If you need to draw anything other than what you have shown in Part A to assist your solutions, use the space below. Do not add anything to the figures in Part A. Yeah, your answer for Part A should be locked until you go back and check. Alright, so for Part B, first thing I noticed, it says derive, so we're going to have to use an equation that we've found in a previous part of the question or on the equation sheet. Since the previous part of the question was a force diagram, we don't really have any equations from that, so we have to use an equation from the equation sheet to help us solve I and double I in B. B, Part I. The force T2 exerted on the block by mass M by the string. Express your answers in terms of these variables and physical constant. This question is asking for us to derive an expression for a force. So going back to the overall concepts, I immediately think of Newton's second law, F net equals ma. But to use this equation, we need to find a system to apply it to. I'm thinking of making the system these two blocks. Then I don't have to care about tension 1 because that would be an internal force now. So F net of the system is equal to the total mass of 2m plus m times its acceleration. Since the system is in equilibrium, we know that this horizontal net force is equal to 0. So looking at this horizontal net force, we can see that T2 contributes to it, and we know that a component of gravitational force contributes to it. Since T2 and the horizontal component of gravitational force are in opposite directions, we can say that T2 minus mass of 2m plus m times g times sine theta. With this equation, we can move T2 to the left and multiply -1 to both sides to get that T2 equals 3m times g times sine theta. And that is your answer for part BI. B double I. The mass m for which the system can remain in equilibrium. Express your answers in terms of these variables and physical constants. Alright, so we're still dealing with equilibrium, but this time we're trying to find mass, big M. So I immediately think back to Newton's second law again, but this time we're going to use a system of only the big mass. So we can get that F net equals to the total mass times acceleration, but since it's in equilibrium, it equals 0. Breaking down the net force of this system, you can get that the object experiences gravitational force and tension force. Since they're in opposite directions, we're just going to put mg minus m2. It all equals 0 because the sphere is in equilibrium. So moving T2 to the side, we get T2 is equal to mg. And we actually found an expression for T2 from part BI. So we can substitute that in and get 3mg sine theta equals to mg. We can cancel out g from both sides to get that m equals 3m sine theta. And that is your answer for part B double I. Alright, part C. This looks like a long question. Now suppose that mass m is large enough to descend and that the sphere reaches the floor before the blocks reach the pulley. Answer the following for the moment immediately after the sphere reaches. Getting a grasp of the overall system, m is falling down, the two blocks are moving up the ramp, and then m reaches the ground and hits the ground. So once m hits the ground, as you've probably seen in real life, the string attached to it goes slack, which means that T2 will immediately go to 0. Both block 2m and block m will only experience gravitational acceleration, but they will be moving up the ramp first, and they will eventually start to go down the ramp. Now that we understand the situation, we can go into individual parts of this part C. Ci. Does the tension Ti increase, decrease to a non-zero value, decrease to 0, or stay the same? You know that once the sphere hits the ground, block m and block 2m will only experience gravitational force. So looking at the system small m, if small m only receives gravitational force, so tension T1 decreases to 0. And we don't need a justification for any of these parts. So that's your answer for Ci. C double I is the velocity of a block, mass m, up the ramp, down the ramp, or 0. So once m hits the ground, the block's velocity would be up the ramp because there was a net acceleration up the ramp. So at the moment immediately after the sphere reaches the floor, the velocity of block m is going up the ramp. And that's your answer for part C double I. C triple I is the acceleration of the block, mass m, up the ramp, down the ramp, or 0. So we know that block m only experiences gravitational force, and that's the only force contributing to the acceleration of the block. So we know that gravitational force is down to the ground, split into horizontal and vertical components being parallel and perpendicular to the ramp. We found out that the gravitational force contributes down the ramp and into the ramp. The force into the ramp is negated by the normal force the block experiences. So its net force going along the axis parallel to the surface of the ramp is going down the ramp, which means its net acceleration is going down the ramp, which is your answer for part C triple I. Alright, part D. We get a new scenario. Consider the initial setup in figure 1. Now suppose the surface of the incline is rough and the coefficient of static friction between the blocks and the inclined plane is μs. Okay, so now we have to consider friction. Derive an expression for the minimum possible value m that will keep the block from moving down the incline. Express your answers in terms of variables and fundamental constants. Alright, so this question still asks for big M. So I immediately think of the process that we've just used for part B, where we had the value of tension 2 to help us find the value of big M. First, let's look at the system of the sphere, which is the most relevant system for this problem. So F net of the sphere equals total mass times acceleration, and this will also equal 0 because we want to find the value of M that will keep the system in equilibrium. So breaking down the components of the net force, we have the force due to gravity, and we have, again, the tension force. So moving T2 to the side and dividing G on both sides, we can get that M equals T2 over G. But now we have to find T2 because we can't use that as a variable because the question didn't say we can. So to find T2, we go back to the process of part A. We're going to use the same system that we used in part A, which is these two blocks. F net of those two blocks is equal to the total mass times its total net acceleration, which is 0 again because we're keeping the system all in equilibrium. Breaking down the net force of the system, we know that the net horizontal force is 0 and the vertical net acceleration is 0, but we're more focused on the horizontal component. So the horizontal component consists of tension 2 and again gravitational horizontal component, which is 2m plus m times g times sine theta. We have to consider friction. So we're finding the bare minimum value m. So if m were a bit smaller than the value that we're looking for, the blocks will start moving down the ramp. So if the blocks start moving down the ramp, friction would need to be up the ramp to prevent this from happening. So it's in the direction with T2, so we're going to add friction. And friction is the coefficient of friction times normal force, which is coefficient of friction, mu s, times the total mass of 3m times g times cosine theta. So if we move t to the left, multiply both sides by -1, we get T2 equals 3mg sine theta minus mu s 3mg cosine theta. Alright, so we have to plug this value of T2 into this equation. So T2 over G equals 3m sine theta minus 3m mu s cosine theta. And we can take the 3m and combine these two. So to make everything neater, we can write that m equals 3m times sine theta minus mu s cosine theta. And that is your answer for part D. Alright, part E, last part. And we get another scenario. The string connecting block M and sphere mass M then breaks. and the blocks begin to move from rest down the incline. The lower block starts at a distance d from the bottom of the incline as shown in figure 1. The coefficient of kinetic friction between the blocks and the inclined plane is mu k. Derive an expression for the speed of the blocks when the lower block reaches the bottom of the incline. Express your answers in terms of the variables and fundamental constants. So for me personally, whenever I see anything sliding down a ramp and we need to find speed, my mind immediately clicks to conservation of energy. So that's going to be my approach for this problem. So with conservation of energy problems, I like to explicitly write conservation of energy so that the grader has an easier time identifying that I know this concept and I am using this concept. Alright, so conservation of energy says that initial energy equals final energy. So initially the blocks are at rest, so their initial velocity is 0, which means that they have no initial kinetic energy. But they are at a height, so they have potential energy. So we're just going to say that they are both at some height h. So their initial potential energy is going to be 2mgh plus mgh, and they don't have any other energy. So for the final position, when the lower block is at the bottom of the incline, both blocks don't have any potential energy, but they do have kinetic energy. So they'll be moving at the same velocity, but their total kinetic energy would be 1/2 2mv squared plus 1/2 mv squared. And since there is friction involved, some energy will be lost due to friction. So we don't use the kinetic energy equation and we don't use the potential energy equation. Whenever we are dealing with energy loss due to friction, we go to the work equation, which is work equals delta kinetic energy, which is the kinetic energy lost, equals force times distance. The distance the blocks travel, which is d, because that is the distance from the bottom of the ramp to their initial position. So for the value h, we can solve that using d and theta. If we draw this triangle, we know that block 2m starts at a height of h. And using this right triangle relationship, we know that sine theta equals h over d. And move d to the side to get d sine theta equals h. So we can plug that into the equation and combine terms. So we can plug that into the equation. Now we have to find the frictional force of the blocks. So the frictional force of each block is different, but in general, the frictional force equals to mu k times the normal force, which is mass of the block times gravity times cosine theta. And we're going to have to split this energy loss due to friction into two parts: energy loss due to block small m and energy loss due to block 2m. So plugging in all these values into the equation below and combining terms, we get that the left side is 3mgh, which can be written as 3mgd sine theta equals, so right side is 1/2 and 2 cancel out, mv squared plus 1/2 mv squared, which is 3 over 2 mv squared plus, so now we have to split the energy loss due to friction from block m and block 2m. Friction from block m is mu k times m times g times cosine theta. Don't forget to multiply d plus mu k times 2m times g times cosine theta times d. Obviously we can combine these two parts, and since each component has m in it, we can everything. So we can get that 3gd sine theta is equal to 3 over 2v squared plus mu kg cosine theta d, and it's cancelled m, it's 3. Alright, I've cleared some space. So we can minus this component on both sides and divide everything by 3 to get that gd sine theta minus mu kg cosine theta times d is equal to 1/2 v squared. So multiply 2 on the left, we get that v squared is equal to 2 times, we can plot gd from both components to get 2gd times sine theta minus mu k cosine theta. So we take the square root of both sides to get that v equals root 2gd times sine theta minus mu k cosine theta. And finally, that is your answer for part E. If you're still confused about how in the world did I figure out, oh, this problem needs kinematics, or this problem needs Newton's second law, the link in the description leads you to a Google Doc of my categorization of each year's FRQ question overall, and each part of each FRQ question's concepts. And each big concept will lead you to an explanation of how I identify a problem needing to use this concept. I hope I've helped you understand this question better, and I'll see you in the next explanation video. Bye bye!